Electromagnetic waves are what allow us to see this magnificent world. It is a spectral family with different wavelengths, including visible light. Scientists utilize electromagnetic waves of different wavelengths to measure objects of different sizes, allowing humans to explore the past and predict the future. Synchrotron radiation was first observed in 1947 at the General Electric Research Laboratory in the United States when scientists were operating a synchrotron accelerator. Its notable characteristics include a small cross-section, high brightness, continuous spectrum from the infrared region through the visible, ultraviolet, and into the X-ray region. The world has come to recognize the significance of synchrotron radiation in science. An enormous amount of resources have been invested to build brighter light sources around the world. The Taiwan Light Source, TLS, and the Taiwan Photon Source, TPS, of the National Synchrotron Radiation Research Center, NSRRC, were completed in 1993 and 2016. Their exterior architectural structure and core facilities were designed and built by the NSRRC team. TPS and TLS are among the brightest synchrotron light sources in the world. More than 2,000 experimental projects are performed at NSRRC every year. Outstanding scientific publications and accomplishments accumulated over the years have put the NSRRC on par with leading large-scale experimental facilities worldwide. How is synchrotron radiation generated? Let's look inside the TPS. The journey begins at the electron gun, where electrons are emitted and accelerated to an energy of 90,000 electron volts into the linear accelerator. The linear accelerator increases the electron energy over 1,000 times to 150 million electron volts, making the electrons travel close to the speed of light. Through the transfer line, the electron beam is then injected into the booster ring, where the energy is increased to 3 billion electron volts. The booster ring increases the electron beam energy to 3 billion electron volts using a radio frequency cavity to supply the energy for acceleration. Finally, the electron beam enters into the storage ring, which contains a number of dipole, quadrupole, and sextupole magnets, as well as insertion devices. Dipole magnets bend the path of the electron beams around the ring, and it is here where synchrotron light is emitted tangentially to the synchrotron orbit. The synchrotron light is guided to the beamlines, where optical components are utilized to select appropriate photo energies and focus beams at end stations for research purposes. When the synchrotron light irradiates the sample, it interacts with matter and produces scattering, diffraction, imaging, or spectral information to investigate the physical, chemical, or biological properties of the sample. TPS is the latest generation of synchrotron radiation in Taiwan. The NSRRC has built and planned numerous beamlines and experimental facilities to promote studies in biomedicine, clinical treatment, materials, green energy, and semiconductor, working towards the goal of establishing Taiwan as a world-class research hub. Synchrotron radiation applications are closely related to life. Take biomedicine, for example. By studying protein structures of viruses and pathogens, the invention of new drugs and vaccines is accelerated. Synchrotron radiation allows a clear view of cancerous cells and helps develop innovative treatment strategies. It even allows an insight into ancient organisms, including dinosaurs from the Jurassic period, through protein sequencing. The NSRRC scientists have developed a fast detection technology for diagnosing multiple types of cancer at an early stage. The distribution of cancer cells distributed within the tissue section can be visualized through the contrast in wax-labeled infrared images. Along with intelligent analysis software for pathological images, physicians are able to obtain early diagnostic evidence for patients to receive optimal treatments promptly. Scientists are pushing the limits of the microscopic world through the power of synchrotron radiation. Investigating the structures of spiderwebs is an example that inspires industries to mimic living organisms and develop new composite materials. Air pollution is generated by small microscopic particles called PM 2.5. Knowing their structure and composition provides more reliable data for smog control and intervention. Carbon dioxide is one of the main causes of global warming. By using dynamic X-ray real-time detection technology, a new catalyst has been successfully developed. It could replace the existing precious metal catalysts because they are more efficient at removing carbon dioxide, use less energy, and are cheaper to produce. Taiwan's semiconductor industry upholds a world-leading position. The NSRRC is located near many of these leaders in the Hsinchu Science Park. For years, the NSRRC has worked closely with these companies, supporting advancements in fabrication processes, resulting in better integrated circuits. From fundamental science to industrial applications, the NSRRC plays a key role in facilitating technical breakthroughs. This light will become a platform for seeking truth and knowledge. This light will inspire more scientists to pursue advanced interdisciplinary research. This light will lead mankind to a brighter future.